Hello everyone, this is our machine learning project, plant seedling classification. Our team member consists of myself, Nan, Brian and Jasly. We will first go through an introduction, followed by data analysis and different machine learning methods we use in our project, and finally, conclusion. The problem statement we picked for our project is the plant seedlings classification from Gaggle. We picked this as we found that we understood its motivation the best compared to the other problems. The motivation of the problem is to classify and differentiate various types of seedlings efficiently. This would allow better crop yields on top of improving environmental stewardship. When we embarked on this project together, we discussed our goals and the things we would like to achieve out of this project. As we are relatively new in the domain of machine learning, we believed that we wanted to take this assignment as an opportunity to learn more about the field and hone our technical skills. Although we acknowledge that getting a higher score for the training is preferable, we wanted to make sure our priority is towards learning so that we can take away as much as we can. With this mindset, we took time to assess and evaluate our methods and implementation carefully. So, the first and the most important task in machine learning is to explore and learn the dataset before proceeding with any algorithms. In our training data, we found a total of 4,750 images belonging into 12 separate classes, and each image has its unique ID and file name. After exploring the data, we will need to split the training dataset for validation. We will use the carrots inbuilt functions, which allows us to instantly get back a dataset from the subdirectories. We then split the trained dataset in the plant seedlings classification directory into 80% training and 20% validation. This could help us get a gauge on our model's performance. Since the directory names within the train directory are the classes themselves, we can then set the arguments labels is equal to inferred to let the functions know that the labels are generated from the directory structure. Since our dataset has different sizes of images, we have also resized the images to 256 x 256 pixels. Finally, we will use this pre-processing technique across all our methodologies as it is simple and easy to implement. Now, I will hand over the time to Jasly, who will talk about our proposed solutions.
I will now be discussing on the different machine learning models that we have used in our proposed solutions. We initially tried to implement traditional machine learning techniques that were taught to us in lectures for this problem. But we soon realized that it would be more efficient and effective to use convolutional neural networks to gather transfer learning instead. So what is convolutional neural networks? It is a class of deep learning neural network models that are popularly used for image classification problems. So how does it work? With the process of applying convolution, which is essentially a weighted sum of the pixel values of the image as the window slides across the image. Turns out, this convolution process throughout an image with a weight matrix produces another image of the same size. We'll be talking about three convolutional neural network models. Firstly, control CNN. Second, MobileNet V2. And lastly, Inception ResNet. For the control CNN model, we decided to use it as a base, as the control. This will allow us to compare the other models that we will be implementing to this mode. We first start off by rescaling the image's shape in the input layer, followed by a sequence of convolutional layers with max pooling, and finally, an output dense layer of 12 neurons with softmax activation function. Here is the architecture of the control CNN model. After implementing the control CNN model, we realized that we faced some challenges, one of which was that most implementations done by others were just utilizing a basic CNN model. We wanted to try out different implementations in our experiment so that we can get the best outcome. So this was really a minor roadblock for us. We managed to overcome this by implementing methods we learned in another module called Neural Networks and Deep Learning. Conclusively, we managed to formulate a MobileNet v2 and an Inception ResNet v2 implementation on top of the basic CNN implementation that we have researched on. MobileNet v2. MobileNet v2 is a relatively lightweight CNN model that is optimized to perform well on mobile devices. In our experiments, we allowed the network to learn and train from the seedling dataset and evaluated its validation accuracy. Our implementation for this model is straightforward, having an input layer with no rescaling, followed by the MobileNet v2 model. Instead of having an output layer right after the MobileNet v2 model, we decided to add in an additional dense layer of 128 neurons with ReLU activation function to further reduce the training loss. Finally, we added another dense layer of 12 neurons with the softmax activation function. Here is the architecture for our MobileNet v2 model. As you can see, for a stride of one block, we have an input layer followed by a ReLU 6 convolutional layer, which will then pass to a ReLU 6 device layer. Subsequently, we have a linear convolutional layer before going into the addition layer. With stride of two blocks, we have an input layer followed by a ReLU 6 convolutional layer. This would then be passed to a device layer, which is a ReLU 6 with two strides. Subsequently, it will be passed to a linear convolutional layer. Inception ResNet v2. Inception ResNet v2 is a CNN model that has already been trained with images from the ImageNet database. Although the network is already pre-trained, we still continued to train it further with the seedlings trained dataset instead of just freezing the entire model. The reason for that is that even though it has already been trained with images from the ImageNet database, it is still foreign to the images found in the seedlings dataset. Since the ImageNet database has a very diverse set of images, we would like to further let the model learn about the actual images from the seedling dataset. This is to narrow down the search limit towards our dataset. Implementation for this is also similar to the MobileNet v2 model above, having an input layer with no rescaling, followed by the Inception ResNet v2 model. An additional dense layer of 128 neurons with a ReLU function activation after the Inception ResNet base model, and finally a dense layer of 12 neurons with the softmax activation function. Here is the architecture for our Inception ResNet v2 model. Firstly, we have the input image layer, followed by a stem layer. This will then be passed into a 5 times Inception ResNet, followed by a reduction. Afterwards, it will be passed to a 10 times Inception ResNet, followed by another reduction, before going into a 5 times Inception ResNet. After that, there will be average pooling, and then a dropout, and we would like to keep 0.8 before going into the softmax activation function. With that, I would now like to hand over the time to Brian, who will be talking about our experiments and results.
Since the seedlings training dataset is already categorized in their respective directories, we can make use of the Keras built-in function to directly generate the training and test datasets, which are 80% and 20% respectively. Since the directory names within the train directory are the classes themselves, we can set the argument labels equals to inferred to let the function know that labels are generated from the directory structure. For a fair comparison, we set the same training parameters for all the models. We use the Adam optimizer with the sparse categorical cross entropy loss function and trained it for 10 epochs with a batch size of 32. For the control model, we can see from the graph that the model starts to overfit. We got a very good training loss and accuracy, but it isn't performing as well for the validation set. Moving on to the MobileNet v2 model, the model is also overfitting too much to the training set, as seen from the high training accuracy and low validation accuracy. Lastly, the Inception ResNet v2 model performs the best among the three models, as seen from the relatively high validation accuracy and low validation loss. In conclusion, we decided to use the Inception ResNet v2 model for our Kaggle submission, and the score we got was within the top 62 percentile. We believe that we could further improve the model's performance by training it for more epochs and adding more dense layers after the base model. We could also add in more dropout layers and introduce callbacks such as early stopping or learning rate scheduler to prevent overfitting from happening like it did with the other models. Thank you.